Welcome to ElectroTuts. In this video, we will look at some questions related to static timing analysis that are frequently asked in interviews for digital profile. So let's get started. I will start with the basic stuff and questions will keep getting more and more interesting as we progress. So here is our first interview question. What is setup time? What is hold time? Why do we have delays in a circuit? What is setup time constraint? What is hold time constraint? These simple questions are generally asked by interviewers to know if you are familiar with the terms. A one-line answer to this question should be sufficient, like the minimum time before the clock edge for which input must be stable is called setup time. Similarly, the minimum time after clock edge for which input must be stable is called hold time. Now let's look at another interview question. Here I have two flip-flops FF1 and FF2 with input given to the first flip-flop and output taken from second flip-flop, and some combinational logic block in between. Considering the delays in the circuit, we have clock to output propagation delay, setup time, hold time, and the combinational logic delay. The question is to find the maximum time period of the clock at which the circuit can operate without any setup or hold time violation. Let's see how to solve these kind of questions. We will start by making the timing diagram of the question, as it will make easier for us to understand what's happening in the circuit. This is the clock signal. Input signal, which is assumed to be stable at least setup time before the clock, such that FF1 doesn't have any setup violation. Due to this input at D1, we will receive output at Q1 after clock to output delay. So Q1 will change and be stable after a delay of T clock to output. This change of signal at Q1 will be reflected at D2 after a delay of combinational logic block, that is TPD. The signal at D2 must be stable at least setup time before the clock edge, so that there is no setup violation in the circuit. This gives us the setup time constraint for our circuit. Consider the time period for our clock to be T. From our discussion, we can conclude that the time it takes for a signal to propagate from FF1 to FF2 plus setup time must be less than the time period of the clock. So we get T clock to output plus TPD plus T setup must be less than or equal to T. In this equation, we know all the delays. So we can find the minimum time period at which the circuit must be operated such that no setup time violation occurs. 1 upon the minimum time period gives the maximum frequency at which the circuit can operate, which was asked in our question. Let me write the question again. We have to find the maximum frequency at which the circuit can operate and check if the hold time violation occurs. Now we will check for hold time violation. From the definition of hold time, we know that the signal at FF2 must not change at least hold time after the clock edge. Therefore, to ensure this, signal at D2 must not change before hold time has passed. So, the delay from clock to output, then from combinational logic, must not change before hold time. So we get the hold time constraint as T clock to output plus TPD must be greater than or equal to hold time. All the values in this equation are available to us. So if the condition is true, we can say that there is no hold time violation and maximum frequency is given by the previous equation as Fmax is equal to 1 divided by T minimum. Now suppose that instead of a single delay value, Both propagation and contamination delays are given. Then how will you proceed? You can simply proceed by thinking about the worst case scenarios. Chances of having setup time violation increases if the delays in this path is more, as the signal will change more closer to the next clock edge, reducing room for setup time, which in turn increases chances of setup time violation. We should consider propagation delay for setup time constraints. Also, data must not change until hold time after the clock edge. So look for the fastest time at which data input to FF2, that is D2, changes. For this we have to consider contamination delay. This equation changes to clock to output delay plus contamination delay must be greater than hold time. This completes the analysis for the question. What generally happens in an interview is that the interviewer keeps on modifying the same question. So let's do the same. What will be the maximum frequency if I introduce a buffer in the clock path of the same question? Let me redraw the question. All the delay values remain same as previous question. Just a buffer is added in the clock path whose delay is TB. Due to the presence of buffer, the clock received at second flip-flop gets delayed by TB units. So if this is clock received at 1, we can draw the clock received at FF2 as the delayed version of clock at 1. This delay is TB. We can see that due to the buffer, we have TB seconds more for the input D2 to get stable, thus reducing the chances of setup violation. From the definition of setup time, we see that the input received by the second flip-flop D2 must be stable at least setup time before the delayed clock's edge received by the second flip-flop. Thus, the setup time constraint becomes T clock to output plus TPD plus T setup must be less than or equal to T buffer plus T. This is T and this is TB. The total delay must be less than this total time taken. This ensures that the signal received at the FF2 is stable at least setup time before the clock edge. Similarly, let's look at hold time constraint. We will be looking at this edge. So the input must be stable at least hold time after the clock edge. Therefore, T clock to output plus TPD must be greater than TB plus T hold. This equation can be used to get the maximum frequency as in the previous case. This completes our analysis. Here also, let's see how to proceed when both propagation and contamination delays are given. Let's again think in terms of worst case scenarios. Reducing this TB increases the chances of having a setup violation. Thus, we consider maximum delay in data path and minimum delay in clock path to take care of worst case that can produce a setup violation. Similarly, from timing diagram, we can see that increasing buffer delay or reducing the combinational logic delay reduces room for hold time, increasing its chances of violation. We can conclude that minimum delay in data path and maximum delay in clock path will increase the chances of hold time violation. So we choose accordingly the values of our delays in the equation. Let's generalize this before moving forward. For setup time constraints, we consider maximum delay in data path and minimum delay in clock path. For hold time constraints, we consider minimum delay in data path and maximum delay in clock path. You can use these or just use basic logic to derive the worst case scenarios for your question using the timing diagrams. Let's go to the next question, which is just the modification of the same question. What will happen if instead of a buffer, we introduce an inverter in clock path? Let's redraw the question. All the delay values remain same as first question, just an inverter is added in the clock path instead of a buffer whose delay is TINV. Due to the presence of inverter, the clock received at second flip-flop gets both inverted and delayed. Here is the clock at FF2. Looking carefully at the timing diagram, we notice that this question is considerably different compared to the previous two questions. While we were considering next clock edge to produce a setup violation in FF2, from timing diagram, we can see that the same clock edge is delayed and received at FF2 and cause setup violation. This is T by 2. Therefore, T clock to output plus combinational logic delay must be stable at least setup time before this clock edge. So we get the setup time constraint as T clock to output plus T PD plus T setup must be less than or equal to Tinv plus T by 2. Notice that in this equation we get T by 2 instead of T as in previous two cases. Analyzing hold time violation in this circuit is slightly tricky and interesting compared to previous cases because of the inverted clock. Let me draw the previous clock edge also. Now, as per hold time's definition, input at D2 must not change before hold time has passed after this clock edge. If this is hold time, here also if this is T hold, then the input D2 must not change until hold time after the clock edge. So I can write the equation as T clock to output plus T propagation delay must be greater than Tinv minus T by 2 plus T hold. This completes our analysis of this question. These three questions cover most of the scenarios you will see in analyzing a digital circuit for timing analysis. If you are preparing for any interview, then you should go over them again and again until you have an in-depth understanding. We will discuss some more questions in my next video. Hit the like button if you found this video useful and subscribe my channel for more awesome electronics related tutorials.